I'm Pasquale, and this is kind of two papers. It's a bit weird because basically it's something we did this year that got the outstanding paper award from a CLUTRR. And then we realized that basically starting from this paper from this year, we can introduce very nicely another paper we did last year at ICML. So it's basically two papers kind of together. And the first one is used to introduce the second one. So yeah, and the first one is about complex experiencing, and the second one is on fully fledged neurosymbolic reasoning. Hope you like them. So first, little motivation on the reasons why we may want to work on hybrid and compositional systems. We all know that machine learning is developing fast, and it will influence many aspects of our lives, like healthcare, recruitment, or for example, credit scoring. And at the same time, AI implies a number of potential risks ranging from discrimination to lack of robustness. And for this reason, there's an increasing need of developing AI systems that we can trust. And for example, this year in 2021, the EU Commission started discussing how to regulate the deployment and use of what they call high-risk AI systems. And they define as high risk the AI system used in, for example, critical infrastructures like transport, educational and vocational training, because they might determine the course of someone's life. So taking discriminatory decisions in, let's say, in kind of in those fields can have an impact on kind of the whole life of individuals in the EU and also outside of the EU, of course. Employment, like recruiting and CV sorting for the same reasons. And essential private and public services like credit scoring and healthcare. And the EU Commission is considering to subject these AI systems to a number of quite strict regulations. For example, by enforcing them to have risk assessment and mitigation systems in place, to be trained from curated datasets to avoid, let's say, exposing those systems on, let's say, biased data, but they don't really define what curated datasets are. But I guess it's something that's hard to kind of to collect at scale. To provide clear explanations for the predictions to the users. And also to have high levels of robustness, security, and accuracy. And now the EU is not an isolated case, like the European Union is not the only one kind of trying to kind of develop a strategy and trying to regulate the deployment of AI systems. And since 2016, there's been a great deal of strategies, action plans, and policy papers proposing national, regional, and international approaches to AI, also outside of the EU, almost in every industrialized country. Now, like the interesting part for me is that those requirements that the EU is planning to impose will automatically disqualify 99.999% of the deep learning models we work on a daily basis, because those systems tend to be very data inefficient and they need large quantities of data to generalize properly. And that it can be very hard to obtain large quantities of curated labeled data. Like it's hard to go through, let's say, millions of documents and making sure they don't contain, let's say, biases or unfair kind of correlations and so on. Because it's very hard to provide guarantees on the predictions of those models, especially when the training distribution and the task distributions differ. Because, for example, when you put an AI system in production, it can also be exposed to, let's say, adversarial data from the users. And it's also very hard to explain the predictions of those models because for example, the activations in a deep learning model do not necessarily correspond to humanly comprehensible reasoning steps. And I think that hybrid and compositional systems can help us here. One second, let me move something. Okay. because they can enable us to design models that can learn from fewer examples, for example, by using strong inductive biases and common sense knowledge. That can generalize even outside of the training distribution, because, for example, they can learn something that looks like symbolic rules and learn to compose them in ways that were not observed during training, and that are also explainable and can provide formal guarantees on their predictions, so to enable their use in critical decision-making tasks. And one work that, in a sense, ticks all of those boxes is this one that we did this year. It's called Complex Query Answering with the Neural Predictors. And this work is based on Eric's MSc project at UCL. And during his MSc thesis, we worked on finding better ways to answer complex logical queries on very large and incomplete knowledge graphs. And this work received an outstanding paper award at CLUTRR 2021. And although I only presented this work in May at CLUTRR, there have been already several companies building on it for their products and extending it in several ways. So I guess most people here might be familiar with knowledge graphs, but yeah, let's briefly introduce them. Let's consider this setting. We have a knowledge graph that is graph structured knowledge base, where knowledge about the world is represented in the form of relationships between entities. In a knowledge graph like this one, nodes correspond to objects in the world, or also abstract concepts, and edges correspond to relationships between these. And in this example, we have a knowledge graph about biomedical entities, which tells us that, for example, paroxetine is used to treat anxiety and has vasodilation as a biological action. That apixaban treats deep vein thrombosis, and one of its pharmacological effects is that it's an anticoagulant, and so on. And one problem with the large-scale real-world knowledge graphs is that they're often incomplete. And in this particular case, for example, we are missing a link stating that, for example, apixaban is a medication, that deep vein thrombosis is a disease. Here there should be a link, but there's not because the knowledge graph is incomplete. And that apixaban can have side effects when taken together with paroxetine. And a very effective solution to identifying missing links in very large knowledge graphs is via neural link prediction models. They're also called knowledge graph embedding models. And the underlying idea is that we can learn an embedding vector for all the nodes in the graph. So in this case, for example, we can learn an embedding vector for apixaban, an embedding vector for paroxetine, an embedding vector for vasodilation, where is that? Here, an embedding vector for deep vein thrombosis, and so on for all the entities in the graph. And now, assume we want to know the type of relationship, if any, between apixaban and paroxetine. The likelihood that two entities, in this case, apixaban and paroxetine, are linked by a given type of relationship, in this case, interacts with, is a function of the embedding vector of the source node. So in this case, the embedding vector of apixaban, and the embedding vector of the target node. In this case, the embedding vector of paroxetine. And we can use this function here for ranking missing links and find out, for example, that apixaban is likely to interact with paroxetine, even if this link is not directly available in the knowledge graph. Because, for example, the model can learn that if you take an anticoagulant together with a vasodilator, you can have side effects. In this case, you have an increased risk of bleeding. Now, consider the problem. Consider a slightly more complex problem. Consider the problem of answering complex queries like this one on an incomplete knowledge graph. In this case, we have a query, which medications have side effects when taken with drugs for treating anxiety. And we want to have a list of medications that answer this query. And this query can be formalized in logic form, and this reads as follows: find M where M is a variable, such that there is a D, which is also a variable representing a drug, such that M interacts with D and D treats anxiety. And this is just an example because our method supports arbitrarily complex logic queries containing conjunctions, disjunctions, and several existentially quantified variables. So up to 2020, up to last year, the best solution for answering those types of queries on very large and incomplete knowledge graphs was the following. So the main paradigm for answering those queries up to last year, basically, was the following. First, we automatically generate millions of complex query answer pairs. So we generate millions of pairs containing the complex query and the answer to the complex query. And then we train a deep neural network to produce the correct answer given the complex query. And the neural network works as follows. First, we represent the complex query as a graph, where each node corresponds either to a variable in the query or to an entity in the query. Then the graph is processed through a deep neural network. And the neural network gives you a ranked list of answers from the most likely to the least likely. So you turn the query into a graph, you feed the graph into a neural network that can be, for example, a graph neural network or one of the architectures proposed in those papers. And the neural network automatically gives you a list of answers. Now, there are two main problems with this approach. One is that training is extremely expensive because the models need to be trained on millions of generated queries. And also, it's not really clear what happens if you evaluate on queries that differ from the queries that you used for training. So it's not really clear what happens if you train on a set of queries containing, for example, only disjunctions, and then you test on some other queries that, for example, only contain disjunctions. And the other is that there is no explanation on the reasons why a given answer was predicted by the model. So you have to trust this black box, and then you can't really check how this black box is working internally. Is there any comment or question up to this part? Okay.
I have a general question, but I will keep it for the end.
Okay, okay, but maybe we can go now. Yeah, okay, we can keep it at the end, as please, no worries. Yeah, basically, what we did is something completely different because we were not really happy with what was being done up to last year, basically. So to solve this task, in this work, we propose a completely new approach. We first train a model phi for answering simple atomic queries, like which drugs treat anxiety. And this model phi is a neural prediction model. So it's a model that is able to, given a link, to score that link, even if that link is missing from the knowledge graph. So we have a model for, we train a model for answering atomic queries, like which drugs treat anxiety. And then after training this model, we convert each complex query into an optimization problem where we need to identify the optimal values for the variables M and D in the query. So M and D here vary in the set of entities. And we try to find the best replacement for the variables M and D that maximize both the likelihood that M interacts with D. This is the embedding of M, and this is the embedding of D. So we try to maximize both the likelihood that M interacts with D, and also the likelihood that D treats anxiety. And then those two likelihoods are aggregated using a T-norm, and that's a continuous relaxation of the logical end from fuzzy logic. So in a nutshell, we translated the complex query answering problem into an optimization problem whose compositional structure is guided by the logic structure of the complex query. So the optimization problem here follows the structure of the logical of the logic query. And depending on whether we search for M and D in a discrete or a continuous space, we can cast these argmax, this maximization problem, either as a continuous optimization problem or as a discrete optimization problem. And here, also because it works slightly better and it's simpler to explain, I think, we will only focus on the discrete version of the problem. Is there any question up to this? Basically, we start with the complex query and we translate the complex query into an optimization objective where the structure of the optimization objective is compositional and follows the logic structure of the query. This is it in a nutshell. Now the problem is finding M and D. So those two M and D are variables, and we want to find the best entities that can replace M and D. If we cast this as a discrete optimization problem, we want to identify the best mapping from variables to entities that maximizes this score here. And we experimented with a very simple greedy strategy to solve this problem. We first start with the variable D, and we search for the k most likely values for D by finding the top k treatments for anxiety according to the Neuralink prediction model. So we take the Neuralink prediction model and we find the top k entities that are most likely to answer this subquery. And k is an parameter defined by chosen by the user. Then for each of the candidate values for D, so for each of the values we found for the variable D, we identified the most likely values for the variable M. Then we have a list of MD pairs. For each of those MD pairs, we compute the score for all generated pairs of values for M and D. So for each MD pair that we obtain after this greedy search, we compute we score the MD pair using this quantity here, using the score of the query. After we replace the variable M and the variable D with those entities. And then return the most likely values for M and D according to the query score given by this quantity here. That is the score of the first subquery, the score and the score of the second subquery joined by a T-norm. This can be, for example, a minimum or a product or something more complex from fuzzy logic. And in our experiments, we experimented on a variety of complex query structures where the target variable here is shown in yellow. And the target variable is connected to the other variables and constants in the query. Here, the variables are shown in blue and the constants are shown in green. And those variables and constants are connected using different patterns by different operators. And for example, we have queries like this one, which medications used for treating fibromyalgia interact with drugs for treating diabetes. Or like this one, for example, which actors played both in which actors played in King's Speech or in Dunkirk, where we also have a logical disjunction operator. And despite being only trained on simple atomic queries, we can see that our model systematically generalizes to complex queries much better than models trained on complex queries in the first place. Here we have the results on freebase 15K237 for different types of complex query types. Here we have the results on freebase 15K. And here we have the results on null. And for example, we can see that for queries containing logical disjunctions, its a tree improves from 0.36 to 0.53, even though we didn't use those queries during training. So during training, we only train on atomic queries, while the baselines are also trained on queries containing logical conjunctions, disjunctions, and so on.
So, but how does it change computationally, the difference between just using the atomic queries and doing an n-hop over it versus embedding the whole query?
Yeah, basically, you need to do this greedy search in a sense, where you start from the anchor node and then you get to the target variable. So in the baselines are basically the baselines embed the complex query into a vector, and then they match the query vector with all the answer vectors. So the baselines are a bit more efficient. While here you need to go from the anchor node to the target node, and so it's a bit more complex. So here you need to call the Neuralink predictor twice, basically. So it's slightly more expensive. And also you have to keep a beam of possible values for, let's say, D and M. So also in terms of space requirements, is maybe a bit more expensive, but in terms of predictive accuracy, it's like you get a large boost. And there are also other aspects where you also get a boost, but let's get there. So basically, computationally, it's a bit more expensive at this time, but the training time, there's no comparison. Basically, at training time, our model is much faster.
I think the inference time is where it'll take longer, right?
Mm-hmm. Yeah, and then you might have a slightly higher memory footprint, basically, because you need to keep this beam of values for each of the variables.
Thank you.
But, yeah, it's something unfeasible. It was doable in our case, at least. And here we have the average results between all types of complex queries that we considered, and we can see that our model produces significantly more accurate results on all the 3 datasets. And this improves over the existing models, both in terms of data efficiency, because we only need to train on a much smaller data set of atomic queries. And also in terms of out-of-distribution generalization, because we get better generalization accuracy on complex queries without having to train on them in the first place. So we only train on atomic queries, but we're able to generalize to complex queries better than methods that train on complex queries in the first place. And another really nice feature of this model is that it can provide explanations for its predictions. So other models in this space only give you a list of answers to the query, right? For instance, in this case, let's say you are using, let's say, Query2Box or GQE. The model gives you a list of answers. Let's say the model gives you apixaban, amitriptyline, duloxetine, and so on, without any kind of further explanations on why the model is giving you those predictions. While this model that we proposed can also be used to provide the intermediate results associated with each query in the form of the variable assignments used to produce the answer. For example, here we can see that for apixaban and amitriptyline were considered as valid answers because, according to the model, they interact with the paroxetine, while duloxetine was considered as a valid answer because, also according to the model, it interacts with the pregabalin. And this enables us to check whether the results are being produced for the right reasons. And in this case, everything is fine because you can verify that apixaban interacts with paroxetine. For example, if you check drug bank, you can see that apixaban interacts with paroxetine. And also paroxetine and pregabalin are 2 possible treatments for anxiety. So the model is giving you the right answers for the right reasons. And and in case you can ask, for example, an expert to validate the predictions, and the expert would be able to validate whether the model is giving you the right answers for the right reasons. And in case the model is giving you the right answers for the wrong reasons, you are able to find out that's happening, and you are able to, let's say, fix that, for example, by augmenting the nudge graph or by adding more supervision signal to the neural link predictor. While with the other models, you cannot really check that. With other models, the model might be giving you the right predictions for the wrong reasons, but you are not able to find that out, basically. So to summarize, in this paper, we proposed a novel approach for answering complex queries on large scale and incomplete nudge graphs. In this approach, we first trained a neural link prediction model on the task of answering simple atomic queries. And then we cast the problem of answering complex queries as an optimization problem, where we need to find the mapping from variables to entities that maximizes the score of the complex query. And we show that this approach that we propose generalizes extremely well to complex queries, despite not having been trained on them in the first place. And all source code, pre-trained models, datasets, and whatnot are online at this link. Please check it out if you're interested in working in this space. And likewise, if you want to collaborate on this topic or have any questions and comments, please poke me or others that Eric, Daniel, or Michal, because we are still keeping to work in this area. Do we want to chat a bit about, before I use this to kind of go to the neurosymbolic reasoning part?
Maybe I have one question on some of the bits you've done so far. So in the QAS optimization problem where you have this research to find the M's and D's, right? Does it always convert to the optimal values for M and D, or does it really matter?
Once again?
I'm asking if, yes, on this slide, you use a greedy search to find M and D, right? My question is, does it always converge to the optimal values for M and D, or does it even matter if it converges to an optimal value or not?
Thanks. So basically, you get the best value for M and D if K is big enough, because this is a kind of a greedy search problem. So first you find top K candidates for D, and then for each of those candidates, you check what's the corresponding value for M. And if K is high enough, basically, and trivially, if K is number of entities, then you always get the best MD pair, basically. But basically, it depends on K, I guess.
Okay, so you treat K as some kind of hyperparameter when you're training the model.
Yes,
right?
yes.
Okay.
And in general, the higher the K, the better the results.
Okay, and does it need to scale, for instance, with the size of your knowledge graph?
So basically what worked in our experiments was, for example, 1,000, but I guess it depends on the query, because if you have, for example, if here you have, let's say, millions of treatments for anxiety, but very few of those treatments for anxiety kind of interact with interact with other medications, then basically the optimal K might be very, very big. So I guess it depends on the query, but typically if you, if K is high enough, basically you can get the optimal values for MND.
Right, thanks.
What else? Yes. Is there any other comment or question? Or maybe, so basically now we have a tool for answering conjunctive queries and also disjunctive queries containing the conjunctions and disjunctions. But for the For the second part, the important thing is that we can solve, like we can answer conjunctive queries. And basically, after we worked on this project on CQD, we realized basically that basically you can implement a fully fledged neurosymbolic reasoning system. Can I go ahead with this? Is it safe?
Yes, please do.
Okay. And hopefully this we get like less time because we already have most of the machinery basically for this other project. So yeah, this is a related project I worked on in 2020, which is about developing an efficient neural version of a symbolic reasoner. So to allow logic reasoning processes to happen instead of a neural architecture. And then I wanted to mention this project because it shows that starting from what we did for answering complex queries, we can implement a fully fledged neurosymbolic reasoning system, which is able to perform complex reasoning tasks and also explain its predictions to the user. So what we used as a starting point for this project was backward chaining. And backward chaining is a logic inference method where you, in a nutshell, you work backwards from the goal. Here's an example of inference via backward chaining. Here we have a query that we want to answer. Here the query is Rick the grandparent of Morty? Then we have a set of facts that we know to be true. Here, the facts are that Rick is the parent of Beth. Beth is the parent of Morty. Beth works as a veterinarian, and so on. This is from the Rick and Morty series. So if you already are familiar with Rick and Morty on Netflix, then this is easier in a sense. And then we have a rule. And the rule says that if X is the parent of some Z, and Z is the parent of Y, then X is the grandparent of Y. And in backward chaining, the first thing we do is checking whether the goal that we want to answer is already contained in the set of facts that we know to be true. In this case, we can see that the goal that we want to answer is not already contained in the set of facts. Then in backward chaining, we check whether there's some rule that can be used to prove whether the query that we want to answer is true or not. And here we can see that we can use this rule for proving that Rick is the grandparent of Morty by replacing the variable X with Rick and the variable Y with Morty, and then checking whether the premise of the rule is satisfied. Because if the premise of the rule is satisfied, then also the consequence of the rule is also true. And the premise is composed by two subgoals. The subgoals are Rick is the parent of Z. There's a Z such that Rick is the parent of Z, and Z is the parent of Morty. And you can see that this is a conjunctive query. So in a sense, I think you can already see where I want to get. So basically, if this conjunctive query admits answers, then the head of the query of the rule is also true, and also this means that the goal is true. So here we have two subgoals. The first subgoal is Rick is the parent of Z, and the second subgoal is Z is the parent of Morty. And those two subgoals can be trivially answered by looking into the set of known facts and setting Z to Beth, because we have Beth that satisfies both the first subgoal and the second subgoal, because according to the facts, Rick is the parent of Beth and Beth is the parent of Morty. So one way you can see backward chaining is as a recursive query or goal reformulation process. So given a query or goal, you either answer the goal or the query right away by checking in the facts that you know to be true, or you reformulate the query into one or more subqueries, And then you try to answer the subqueries recursively. And this is backward chaining in a nutshell. It's a recursive query reformulation process. And backward chaining works very, very well for logical reasoning, but there's a problem. Now, assume the query involves the predicate grandpa, but the facts and the rules in the knowledge base only know about the predicate grandfather. In this case, the classical backward chaining algorithm cannot answer this query because it cannot capture the fact that, for example, grandpa and grandfather are semantically similar. And one way we can solve this problem is by representing the symbols by means of embedding vectors, representing their semantics, and replace equality between symbols with a continuous similarity measure between their embedding vectors. And for example, like the Gaussian kernel. So instead of comparing symbols together, we represent each symbol using an embedding vector. And then instead of comparing symbols together, we compare their embedding representations. And this enables us, for example, to match together grandpa and grandfather, even though their symbolic representations are different because their semantic embedding representations are similar. Here we can see that this vector looks pretty much like this vector. But they're not exactly equal because here the similarity is not 1, but they're very, very similar. So the similarity here is 0.9. We can derive a differentiable version of the backward chaining algorithm that works like this. We start with an embedding of representation of the goal. And also, so we take the goal and we compute an embedding representation for the goal. And we also compute an embedding representation for each of the ground facts that we have in the KB. So the first thing we do is checking whether the goal is already contained among the ground facts. The way we realize this is this contained here. The way we realize this in a differentiable manner was the following. We first compute the similarity between the goal and all the facts in the KB. And then we take the maximum of those similarities. And this operation can be implemented very efficiently using, for example, nearest neighbor search framework. So even if you have millions or billions of facts, there's a way you can implement this process at scale by, for example, indexing all those vectors and then running nearest neighbor search algorithm over all those vectors. So you can make this scale to a very large knowledge base. Then we need to reformulate the goal into one or more sub-goals. And we can see each rule as a component that takes a goal as an input and outputs one or more sub-goals. So both the goal and the sub-goal representations contain dense vectors representing, for example, relation types. And we can learn to generate such dense vectors end-to-end via backpropagation. So instead of rules, we can have neural modules that take the embedding of the query as an input and output the representation, the embeddings of the subqueries. And those components can be trained end-to-end via backpropagation. So in this case, we feed our goal into this module. And this module generates a list of sub-goals, which in fact corresponds to a conjunctive query. Here, the position of the variables is fixed in advance, but everything else, in this case, the predicate in the first subquery, the predicate in the second subquery, and so on, are learned via backpropagation. And we can answer this subquery using the greedy strategy that we discussed at the beginning of the talk by answering each query atoms one by one. And each query atom is answered using the same, so each subquery is answered using the same process that we used for the query. So this process is recursive. You start with a query, you reformulate each query into one or more subqueries using a neural module, and each subquery is answered in the same way as the query, recursively, up to some stopping criterion. Now note that the module that reformulates the goal into subgoals can be trained end-to-end via backpropagation. And this means that we can see how the module is simplifying the goal into subgoals, because we can check how grandpa was rewritten by this module. We can see that, for example, the module is translating grandpa into parent-parent. And this means that we can extract logic rules from this reformulation process, because we can see that the model is translating grandpa with the parent-parent. So we can use this information to extract a logic rule. And then we can also provide those logic rules that we extracted as an explanation to the user.
Pasquale, you have about 2 minutes more.
Okay. Yeah, we can train this module either by classic supervised learning methods or via self-supervision. And one experiment I want to mention is on a dataset called CLUTRR. CLUTRR is a dataset that's explicitly designed to test a model's ability for systematic generalization by evaluating on held out combinations of logic rules. So training instances in CLUTRR can be described as graphs where nodes correspond to family members and edges correspond to family relations. And you need to identify the relationship between two family members by reasoning over the graph. So during training, you see graphs like this one, but at test time, you see graphs that are much more complex. And we evaluated on an extensive set of baselines and did a careful hyperparameter tuning for each of the baselines. And we can see that our model that performs this neurosymbolic model that we proposed, that we called conditional term prover, generalizes very effectively in this setting. And it's also, as a byproduct, it's also able to, you are also able to extract logic rules, because you can inspect each query, how each query is reformulated by the model into subqueries, and you can use this information to extract rules out of the model. So for example, here we can see that grandparent was reformulated into parent-parent, or for example, grandparent was reformulated into grandparent sibling. So for example, if A is the grandparent of B, and B has a sibling C, then A is also the grandparent of C, and so on. So you can also use those rules to explain the results to the user as a byproduct. Yeah, and this also works decently in link prediction tasks. But yeah, I don't think I have too much time to elaborate on this.